Module 7, Lecture A, Object and Properties. By the end of this lecture, you will be able to explain the role of object as the ultimate base class in Python's class hierarchy, define properties using the property built-in or decorators to control attribute access and validation, and use properties to replace direct attribute access in simple classes without breaking client code. The object base class, implicit object inheritance. In Python, almost every class is ultimately based on a built-in class called object. If you define a class without specifying a parent, Python automatically makes it inherit from object. This gives all classes a shared foundation with a common identity and consistent basic behavior. As a result, even the simplest class fits into a unified type system without any extra work from the programmer. In Python, implicit inheritance means that every new class automatically inherits from a basic built-in object class. This is similar to joining a university staff and immediately following the institution's standard rules. Because of this, your class automatically gains fundamental behaviors such as how instances are created, how they are represented as text, and how they are compared. You do not need to define these from scratch, which helps your class integrate smoothly into Python's overall runtime system. In Python, every class you define automatically inherits from a built-in base class called object. This implicit inheritance means all classes share a common starting point and provide a basic set of behaviors, such as identity comparison and conversion to text. Because of this shared base, tools and libraries can reliably work with any class, and your code fits into a consistent class hierarchy. You can later refine or override these default behaviors, but the object class always provides a stable foundation. Python code, implicit object inheritance. In Python, you can demonstrate implicit object inheritance by creating simple classes with and without explicitly specifying a base class. Even if a class does not list any parent, it still automatically inherits from the built-in object type. You can then compare explicit and implicit inheritance by using the isSubclass function to check whether these classes are subclasses of object, and the isInstance function to confirm that their instances are also instances of object. This shows that all new-style Python classes ultimately derive from object, whether or not you state it directly. In this example, we define a class called implicitExample without naming any base class, which is the usual style in Python. Even though no base is specified, the class automatically inherits from the built-in object class. In Python, all classes do this by default, making them new-style classes. This implicit inheritance gives the class a set of basic methods and properties that are shared by all Python objects. In this example, we define a class called explicitExample that directly inherits from the built-in object base class, which is the root of all classes in Python. Writing object in the class definition makes it explicit that explicitExample is a subclass of object, even though this is already assumed in Python 3. This explicit form can improve clarity in your code and was required in older versions of Python, where you had to specify object to get the modern class behavior. This example checks whether the class named implicitExample is a subclass of Python's built-in object class using the isSubclass function. That function returns true when the first class inherits from the second. Because all classes in Python automatically inherit from object, the check confirms that implicit example is a subclass of object, even though this was not written explicitly. The result is then printed to show this inheritance relationship. In this example, we use the isSubclass function to check whether the class called explicitExample is a subclass of the built-in object class. The function takes explicitExample as the first argument and object as the second argument. Since explicitExample explicitly inherits from object, the check returns true. We then print this result to confirm the relationship between explicitExample and the object class. We first create an instance of a class that does not explicitly name a base class, which means it automatically inherits from the built-in object class. Then we create an instance of another class that explicitly states it inherits from the object class. With both instances created, we can compare them to show that despite the different ways inheritance is written, they both share the same underlying base class, which is object. In this example, we check whether an instance of the class implicitExample is also an instance of Python's base object class using the instance function. The check confirms that the created instance is indeed an instance of object. This shows that even if a class does not explicitly inherit from object, it still automatically derives from it. As a result, all Python classes have access to the methods and properties provided by the base object class. We are checking whether a particular instance is an instance of the built-in object class using the instance function. This function returns true when the first value is an instance of the class given as the second value, or of any subclass of that class. Because all Python classes automatically inherit from object, this test confirms that an instance created from a class that explicitly inherits from object is still recognized as an instance of object. This shows that explicit inheritance from object behaves the same as the default implicit inheritance in terms of instance recognition. We are looking at the method resolution order, or MRO, of the implicit example class to see how Python decides where to find methods. The MRO is a sequence that shows the order in which base classes are searched. When we print the MRO for implicit example, it lists the class itself first, and then the built-in object class. This shows that even if we do not explicitly inherit from object, Python still treats classes as part of the same inheritance hierarchy, which keeps method lookup behavior consistent. This script shows how implicit and explicit inheritance work in Python. It defines one class with no stated base class and another that explicitly inherits from the object class. When the code runs, both classes are identified as subclasses of object, and their instances are also recognized as instances of object. The method resolution order for the implicit class confirms it follows the standard inheritance chain. Overall, it demonstrates that in Python, all classes ultimately derive from the object class, which provides a consistent basis for method resolution and attribute access. Modern class model. In Python's modern class model, every class automatically inherits from a common base called object, which creates a single unified hierarchy for all types. This means both user-defined and built-in types share the same fundamental ancestor. As a result, Python can treat many different kinds of values in a consistent way, while still allowing you to customize how each class behaves. In Python, the modern class model provides a single consistent way for the language to handle things like attribute lookup, method resolution, and converting objects to strings. Because all classes inherit from a common root, Python can use one unified mechanism to determine which methods to call and how objects behave. This shared foundation makes class behavior easier to understand and enables advanced patterns such as multiple inheritance and mixins to work reliably across the language. In Python, the modern class model makes user-defined classes behave much more like built-in types. Because all classes share a common base, they fit smoothly into the language's core features and work well with libraries and frameworks that expect standard object behavior. This means a custom class, such as one representing a sensor, can be logged, serialized, and inspected just like built-in objects. Overall, this unified hierarchy encourages creating rich, domain-specific classes that still act consistently within the language. Python code, modern class model. This section demonstrates the modern class model where objects implicitly inherit from base classes. It shows that different user-defined classes ultimately share the same top-level ancestor in the class hierarchy. The goal is to highlight that both user-created classes and built-in types follow this same inheritance structure. This consistent behavior helps unify how we understand and work with all objects in the system. We define a class called bank account to represent a bank account with two main pieces of information. When a new bank account is created, an initializer method runs and takes the owner's name and the account balance in dollars as inputs. Inside this method, the owner's name is stored in an attribute called ownerName, and the balance is stored in an attribute called balance$. This lets each bank account object keep track of its own specific owner and balance. This method specifies how a bank account object is turned into a readable string. It creates a formatted message that includes the account owner's name and the balance in dollars. As a result, when the object is printed or logged, it appears as a clear, human-friendly description of the account. The data pipeline class represents a sequence of processing steps. Its initializer, or constructor, runs when a new pipeline object is created. This initializer takes a single input called the number of steps, which tells how many processing stages the pipeline has. That value is stored inside the object, so each data pipeline instance keeps track of its own step count. The string method of the data pipeline class returns a short text description of a data pipeline object. When this method is called, it produces a formatted message that explains the current instance. In particular, it reports how many processing steps are configured for that pipeline, using the stored count of steps. This makes the object easy to understand when it is printed or converted to a string. We create a new bank account object by giving it the owner name Alice and an initial balance of $1,500. This sets up the account with those values stored as its attributes. When we print the account, the string conversion function is called, which uses a special method in the class to produce a nicely formatted description. That description includes the owner's name and the current balance of the account. We create a new data pipeline object and pass in the number 3 to specify that it has 3 processing steps. This sets up the pipeline with its internal step count set to 3. We then print the pipeline, which calls its string method. That method returns a descriptive message indicating how many processing steps are configured in the pipeline. We print a message to indicate that we are about to show the method resolution order for the bank account class, then call a method resolution order function on that class. This function returns a list of classes that defines the order in which Python searches for methods. The search starts with the bank account class itself and then moves up through its ancestor classes. Viewing this order helps us understand how inheritance works and how Python decides which method to use when several classes define methods with the same name. We begin by printing a short message to indicate that we are about to show the method resolution order for the data pipeline class. Then, we call the function that returns this order for that class. This function produces a list of classes that Python will search in sequence when it looks for methods. The result confirms the inheritance path for data pipeline and shows that it ultimately includes the base object class. This illustrates the modern Python class model, where every class implicitly inherits from object. The code checks whether the bank account and data pipeline classes both ultimately inherit from Python's base object class. It prints a message asking if object is their ultimate ancestor, then inspects the method resolution order of each class. By confirming that object appears there, it shows that both classes follow Python's modern class model. This means they implicitly inherit from object, just like built-in types, which helps ensure consistent behavior across the language. This Python script illustrates the modern class model by defining 2 simple classes, one representing a bank account and another representing a data pipeline, each with an initializer and a method that returns a descriptive string. When you create and print a bank account for Alice with a balance of $1,500 or a data pipeline with 3 steps, you see readable descriptions of those objects. The script then inspects the method resolution order for both classes and shows that they ultimately inherit from the base object class. This demonstrates that user-defined classes and built-in types in Python share a common inheritance structure rooted in the object class. Method and attribute effects. In Python, every modern class automatically inherits from a built-in base class called object, which provides a common set of methods and attributes. You usually do not call these methods directly, but they control important behaviors such as checking an instance's type, printing an object, or comparing 2 objects. This base class acts as a shared foundation so that all user-defined classes support a minimal, predictable interface. As a result, Python can treat user-defined and built-in objects in a consistent way, even when they come from different libraries or domains. When a Python class inherits from the base class called object, it automatically gets default behavior for things like how it is represented, how it is compared, and how its memory is managed. If you do not define your own representation, Python shows a generic form with the class name and memory address. By default, objects are compared by their identity in memory, not by the data they hold. So two objects with the same information are not considered equal unless you define what equally means for them. Inheriting from object gives your classes a consistent foundation that you can customize to match your specific needs. In Python, the base class called object underlies all classes and enables advanced attribute access and introspection. Because every class inherits from this single base, Python can use a consistent protocol to look up attributes and understand what an object can do at runtime. This uniform behavior lets tools, frameworks, and debugging environments inspect user-defined objects, list their attributes, and work with them without knowing their internal details. As a result, different parts of a system can integrate more easily, since all objects follow the same foundational model established by the base class. Python code, method and attribute effects. The object base class supplies default methods for all classes, including how objects are represented as text and how they are compared for equality. Before overriding these methods, objects use this built-in behavior, which often shows only basic information like the type and memory address, and treats different instances as unequal even if their contents match. By overriding the representation and equality methods in a subclass, you can change how objects are displayed and how equality is determined, while still relying on the object base class to provide the initial baseline behavior. We define a class called book that uses an initialization method to set up new book objects. This method takes a title and a page count as inputs. It stores these values in instance variables, so each book object keeps its own title and number of pages. This structure makes it easy to create and manage many different books, each with its own information. We create an instance of the book class called Book A with the title Python Basics and a page count of 300, which initializes an object with these attributes. Then we create a second instance called Book B using the same title and page count. Although Book A and Book B have identical attribute values, they are still two separate objects in memory. These two instances will be used to show how Python handles the default representation of objects and how it checks whether objects are considered equal. The first line prints the default string form of the book object, which comes from the base object class and usually shows its type and memory address because the book class does not define its own representation method. The second line compares the two book objects for equality. Since there is no custom equality method, this comparison only checks whether both variables refer to the exact same object in memory. They do not, so the result of the comparison is false. In the BetterBook class, the constructor method called init sets up each new book object with two attributes, title and pages. The title attribute holds the book's name, and the pages attribute stores how many pages it has. By assigning these values when the object is created, every BetterBook instance has its own specific title and page count. This allows us to represent different books as separate objects with their own properties. In the BetterBook class, the representation method is defined to give a custom text description of each object. It returns a formatted string that includes the class name, along with the book's title and number of pages. This makes the object's output more readable and informative. Such a custom representation is especially helpful for debugging and logging because it clearly shows the key details of the object when it is printed or inspected. This method explains how two better book objects are checked for equality. It first verifies whether the other object is also a better book. If not, it signals that the comparison is not supported. If the other object is a better book, it compares their title and pages attributes. The method returns true when both of these attributes match and false otherwise. We create an instance of the Better Book class called Better A, giving it the title, Python Basics, and 300 pages, which sets up an object with custom behavior for how it is represented and how equality is checked. We then create another instance, Better B, with the same title and page count. Because the class overrides the default methods from the base object class, we can compare these two instances using our own logic. This demonstrates how custom definitions of equality and representation can change how objects behave compared to the default behavior. The first line shows a custom text description of the Better Book object by replacing the default object method with one that returns a readable string containing the title and page count. The next line checks whether two Better Book objects are equal using a custom equality method. This method compares their title and pages attributes to decide if they represent the same book. Together, these lines illustrate how overriding built-in methods can change how objects are displayed and how they are compared. This script shows how Python's default object behavior works and how to customize it. It first defines a simple book class where two books with the same title and page count are still considered different because the default equality check compares their identities, not their contents, and the default text representation is generic. It then defines a Better Book class that overrides these defaults so that printed objects show a more informative description and equality is based on matching title and pages. This demonstrates how redefining equality and representation methods can make custom classes behave in a more meaningful and useful way. Python Property Basics. Manual Property Creation. In Python, a manual property lets you control access to an attribute through functions instead of using the attribute directly. You define functions to get, set, and optionally delete the value, then combine them into a property object attached to the class. Other parts of the program still use it like a normal attribute, but your custom logic runs behind the scenes. This is useful for adding validation, logging, or computed values without changing how existing code accesses the attribute. To manually create a property in Python, you choose a public attribute name and a separate internal name, often starting with an underscore to store the actual data. You then write one function to get the internal value and another to set it, adding any checks or transformations you need. You can also define a function to handle deleting the attribute if that is required. Finally, you pass these functions to the property constructor and assign the resulting property object to the class using the public attribute name. Manually creating properties is useful when you need strict control over how an attribute is accessed, such as a bank balance or product price. By using getter and setter functions, you can enforce rules like blocking negative values or converting units, which keeps behavior consistent. This lets you start with a simple attribute and later add validation or logging without changing how the attribute is used. As a result, you can design classes that are both easy to use and carefully control how their data is managed. Python code. Manual property creation. This section explains how to manually create properties using getter and setter functions so that attribute access is controlled and validated. It shows how internal attributes are used to safely store the checked values behind the scenes. Finally, it prints out the results to clearly demonstrate how the property behaves when values are read and updated. In the bank account class, the constructor sets up a new account by first creating an internal balance attribute marked with an underscore to show it is for internal use and initializing it to 0. It then assigns the user's starting balance through the public balance property, rather than changing the internal value directly. This approach ensures that any validation or safety checks built into the property are applied when the starting balance is set. The getBalance method is used to access the current account balance in a controlled way. It simply returns the value stored in the internal balance attribute, which holds the actual balance data. This method is part of a manual property setup that keeps the internal state hidden while still allowing other parts of the program to read the balance safely. This setter function updates the account's internal balance while preventing invalid values. It first checks whether the new amount is below 0, and if so, it raises a value error so the balance cannot become negative. If the amount passes this check, the function converts it to a floating point number and stores it as the new balance. Using a floating point value helps maintain precision in financial calculations. We manually create a property for the balance using a property function that takes a getter and a setter method. The getter returns the current balance, and the setter checks and updates the balance value. By routing all access to the balance through these methods, we can control and protect how the balance is read and changed. We also attach a short documentation string to explain that this property securely manages the account balance. We create a new bank account object with a starting balance of $100, which calls the constructor. The constructor first sets the internal balance to 0, then uses a setter method to apply the starting balance. This setter checks that the balance value is valid before updating the internal attribute. When we access the balance property to print the starting balance, the getter method returns the current balance, and it is displayed as starting balance $100. The code sets the bank account's balance to $150 using a property, so the setter function runs automatically to validate and apply the new value. After this update, the program prints the balance, confirming that it is now $150. We try to set the account balance to a negative value, which activates the setter method. This method checks the new balance and raises a value error if it is negative. We wrap this operation in a try-except block so the program can handle the error instead of crashing. When the exception is caught, we print a message that the attempt to set a negative balance failed along with the error details. This script shows how to manually create and use properties in a Python class to control access to an internal value. A bank account class stores a balance starting at $100 and uses a getter function to read this value. A setter function updates the balance, but first converts the input to a floating point number and checks that it is not negative. When you set the balance to $150, it is accepted and stored. But trying to set a negative balance causes the setter to raise an error that is caught and reported. This demonstrates how properties can enforce validation rules and protect the integrity of data inside a class. Property decorators explained. Property decorators let a class define attributes whose access is controlled by methods without manually creating property objects. When you mark a method with this decorator, it decides what happens when the attribute is read, allowing dynamic computation or enforcing rules. From the outside, the attribute still looks like a normal field accessed with dot notation. This makes it easy to start with a simple attribute and later add validation or logic without changing how existing code uses it, keeping the class interface clean and intuitive. In addition to the basic property decorator used for reading attributes, Python provides decorators for setting and deleting them. These decorators are attached to methods with the same name as the property, but marked as setter or deleter. When you assign a value, Python calls the setter method, which lets you validate or transform the input in one central place, such as enforcing that an interest rate stays within a valid range. A deleter method can similarly control what happens when an attribute is deleted, such as handling cleanup or blocking deletion, while the attribute still appears simple to use from the outside. Property decorators help keep a class interface simple while allowing the internal implementation to change over time. They let you adjust how a value is stored, calculated, or logged without changing how other code accesses it. For example, an age attribute in a user profile can later be computed from a birth date or instrumented for analytics, and existing code can keep using it the same way. This makes classes easier to maintain and extend because the logic for each attribute stays organized and flexible behind a stable interface. Python code, property decorators explained. This section explains how to use property decorators to control access to an attribute and validate its value while still using simple attribute-style syntax. It shows how a getter method can manage reading the value, a setter method can check or adjust the value before storing it, and a deleter method can handle what happens when the attribute is removed. The example is kept beginner-friendly and includes clear printed output, so you can see exactly when each method is called and how the attribute behaves during normal use. The thermostat class is designed to manage temperature settings. Its constructor initializes each new thermostat object with a temperature value in Fahrenheit. This value is stored in a private attribute, marked with an underscore to signal that it should not be accessed directly from outside the class. Instead, the class is set up so that the temperature can be safely read and changed through property decorators defined later, allowing controlled access and modification. This section describes a property method used to access a temperature attribute. When the temperature is read, a getter method runs, prints a message to show that it is being accessed, and then returns the stored value. The actual data is kept in a private attribute whose name starts with an underscore to signal that it is for internal use. This design encapsulates the temperature value and allows controlled access, making it possible to add checks or modify the data when it is retrieved. This section describes a setter for a temperature property that runs whenever a new temperature is assigned. It announces that it is validating the new value, then checks whether the temperature is between 32 and 212 degrees Fahrenheit, the freezing and boiling points of water. If the value is outside this range, it raises a value error to block the invalid assignment. If the value is within the allowed range, it updates the internal temperature storage with the new value. In this thermostat class, a special deleter is defined for the temperature property, so that attempts to delete it are blocked. When code tries to remove the temperature attribute, the deleter runs, prints a message that it is preventing the deletion, and then raises an attribute error. This behavior stops the temperature from ever being unset, which helps maintain the safety and integrity of the object. We create a thermostat object from the thermostat class and initialize it with a temperature of 72 degrees Fahrenheit. This sets its starting temperature value. We then read the temperature attribute using dot notation, which calls the getter method behind the scenes. The getter returns the currently stored temperature, and that value is printed as the current temperature. We update the thermostat's temperature by assigning it a new value of 75, which activates the setter method. The setter checks that this new temperature is within the allowed range before storing it. Afterward, we print the temperature, which calls the getter method to retrieve the current value. This confirms that the assignment worked, and the thermostat now holds the updated, validated temperature. The example shows what happens when we try to set the thermostat to an invalid temperature. When the code attempts to set the temperature to 10 degrees, the setter method checks the value against the allowed range. Because 10 is below the minimum, the setter raises a value error. The program then catches this exception and prints a message explaining that the value was rejected, along with the error details from the exception. We attempt to delete the temperature attribute from the home thermostat object, which triggers the deleter method for that property. This action is wrapped in a try block so that any error can be handled. The deleter method raises an attribute error, which is then caught in the except block. We respond by printing a message that the deletion was blocked, along with the error details. This shows how the deleter method enforces a rule that the temperature attribute cannot be removed, protecting the object from accidental deletion. This script uses property decorators in Python to control how a class attribute is accessed and changed. The thermostat class stores a temperature in Fahrenheit and uses a getter method that prints a message whenever the temperature is read. A setter method checks that any new temperature stays between freezing and boiling points and raises a value error if it does not. A deleter method blocks attempts to remove the temperature attribute by raising an attribute error. When you run the code, you see messages for each operation and exceptions for invalid actions, illustrating safe and controlled attribute management. Getters, setters, deleters. When working with properties, it helps to think in terms of three roles: the getter, the setter, and the deleter. The getter controls how an attribute's value is retrieved, and it can compute or transform that value before returning it. For example, a bank account's balance might be calculated from its transactions each time it is accessed. This lets the program use the balance without needing to know how it is computed. Keeping a clear separation between how data is stored internally and how it is used externally. A setter works with a getter to control how a property's value is updated, giving you one place to enforce rules and validation. For example, in a class that stores a student's exam score, the setter can make sure the score stays between 0 and 100 and handle any invalid values. In other cases, such as web app settings, the setter can clean up inputs by converting text to lowercase or trimming extra spaces. This centralized control lets you change the rules later without touching the rest of the code, which helps keep behavior consistent and reduces bugs. A deleter is an important part of property management because it defines what should happen when a property is removed. When the property is deleted, the deleter controls the meaning of that deletion and can trigger actions such as clearing caches or updating logs. In simple situations, it may just remove a value from a dictionary, while in more complex systems, it can reset calculations or free resources. Using a deleter helps ensure that all necessary cleanup happens so the object state stays consistent and predictable. Python code, getters, setters, deleters. This example uses a simple temperature value to demonstrate how property getters, setters, and deleters work. The getter is used to read the temperature and can print a message whenever the value is accessed. The setter is used to update the temperature, performing validation and access control so only valid values are stored, while also printing clear feedback. The deleter is used to remove the temperature value and can perform any needed cleanup. Again, showing a message so beginners can easily follow what is happening. Together, these property methods illustrate how to manage access, validation, and cleanup in an easy-to-understand way. The thermometer class is defined to represent a thermometer object, and it includes an initialization method that takes a temperature value in Fahrenheit. This method runs automatically whenever a new thermometer object is created. Inside the method, the Fahrenheit value passed in is stored in a private instance variable. This allows each thermometer object to keep track of its own initial temperature in Fahrenheit when it is first created. This section describes a property method used to access a temperature stored in Fahrenheit. When the method runs, it announces that the getter is being used and then returns the current value of the private temperature attribute. This design keeps the temperature data encapsulated while still allowing controlled access and making it clear when the value is retrieved. The Fahrenheit setter method is responsible for updating the stored temperature value while enforcing a physical limit. When it is called, it first announces that it is validating the new Fahrenheit temperature. It then checks whether the value is below -459.67 degrees, which represents absolute zero in Fahrenheit. If the value is below this limit, it raises a value error to block an impossible temperature. If the value passes this check, the method safely updates the internal temperature storage with the new Fahrenheit value. In this code, the thermometer class includes a deleter for its Fahrenheit property. When this deleter is used, it announces that the stored Fahrenheit temperature is being cleared. It then sets the internal Fahrenheit value to none, effectively removing the saved temperature from the object. This provides a simple way to clean up the temperature data when it is no longer needed. We begin by creating a new thermometer object and giving it an initial temperature of 72 degrees Fahrenheit, which triggers the constructor to store this starting value. We then call the getter method to print the temperature. This getter simply returns the stored Fahrenheit value, showing how it provides controlled access to the thermometer's internal temperature setting. The code sets the thermometer's Fahrenheit temperature to 98.6, which activates a setter method that first checks the value is above absolute zero. If the value is valid, the thermometer's temperature is updated. The code then calls a getter method to retrieve the current Fahrenheit temperature and prints a message confirming that this updated value has been read. When the delete operation is called on the Fahrenheit property of the thermo object, it activates the property's deleto method. This method prints a message that the stored Fahrenheit temperature is being cleared, then sets the internal Fahrenheit attribute to a value of none. As a result, the temperature value is effectively removed from the object. Printing the internal attribute afterward shows that it is now none, confirming that the deleter successfully cleared the stored value. This example shows how a Python class can use properties to control access to a temperature value in Fahrenheit. A thermometer object starts with an initial temperature, and when the value is read, a getter method runs and returns it with a message. When the temperature is changed, a setter method checks that it is not below absolute zero before updating the stored value and printing another message. Finally, a deleter method is called to clear the temperature by setting it to none and announcing that change. Overall, the script illustrates how properties can neatly handle data access, validation, and cleanup inside a class. Encapsulation with properties, validating assignments. Using properties instead of direct attribute access lets a class actively check and control the data it stores. When a value is assigned, the property can validate it, such as making sure an age is not negative or a percentage stays between 0 and 100. This prevents invalid data from slipping in unnoticed and allows errors to be handled right away. As a result, properties turn simple data storage into a validation step that improves encapsulation and makes the class more robust. Using properties to validate assignments is important wherever data accuracy matters. In financial systems, they enforce business rules on account balances and transaction amounts, preventing issues like negative balances or overly large transactions. In medical records, they help ensure that values such as heart rate and medication dosage stay within acceptable ranges. By acting as gatekeepers at the boundary of an object, properties catch invalid data early and keep errors from spreading into reports or external systems. Using properties to validate assignments lets your classes become more robust without breaking existing code. You can start with simple classes that expose attributes directly. Then later, add properties that check values, such as validating email formats or geographic ranges. This keeps the public interface the same while routing all assignments through validation logic. As a result, your codebase gains reliability and fewer bugs without requiring changes to how other parts of the system use these classes. Python code. Validating assignments. This section explains how to use properties on simple account attributes to validate assignments. It shows how you can reject invalid values while keeping the original attribute names the same. It also illustrates how to replace direct attribute access with property-based access without breaking any existing client code that already uses those attributes. The bank account class represents a simple bank account with an owner and a balance. In its constructor, it takes the owner's name and a starting balance. The owner's name is stored directly, so each account has a unique owner, while the balance is stored in a private variable to protect it. The starting balance is set through a balance property, which calls a setter method that checks the value is not negative before assigning it. This design keeps the balance data safe and ensures it can only be changed in a controlled, valid way. This part of the code sets up a property that controls access to the balance in the bank account class. When the balance is requested, the property returns the value stored in a private internal variable. Using a property in this way keeps the balance access controlled and organized. It also ensures that any logic related to getting the balance stays inside this single property method. This section describes the setter for the balance in a bank account class. When a new balance is assigned, the method first checks whether the amount is negative, and if so, it raises a value error stating that the balance cannot be negative. If the amount is valid, it is converted to a floating point number and stored in the internal balance attribute. This design enforces that only non-negative balances are allowed and helps maintain the integrity of the account data. We create a new bank account for an owner named Alice with an initial balance of $100, which calls the constructor to set up the owner and balance. The balance is assigned through the balance property's setter method. We then access the balance property again, this time using its getter method to retrieve and print the current balance. The code updates the account balance to $50 using a special balance setting method that first checks the new amount is not negative. If the amount is valid, it changes the stored balance and then prints a message showing the new balance of $50. This illustrates how using a property for the balance allows controlled changes while protecting the correctness of the account data. When we try to set the account balance to -20, the balance setter runs and checks whether the new value is below 0. Because it is negative, the setter raises a value error with a message saying the balance cannot be negative. Control then moves to the except block, which catches this value error. The program prints the error message, showing that the attempted update was rejected due to the rule that the balance must not be negative. The code prints the account's final balance by accessing its balance property, which returns the current stored value. Using a property allows controlled access to this balance, so any rules or validations are automatically enforced whenever the value is read. The printed result reflects all previous operations and checks that have been applied to the account's balance. This Python example shows how to use a property in a bank account class to validate changes to the account balance. When an account is created, the initial balance is set through the property, which prevents it from being negative. Updating the balance to a positive value works, and the new amount is displayed. But trying to set a negative balance raises an error, which is caught and reported. After this failed attempt, the script confirms that the balance has not changed. This design keeps the balance stored in a private attribute while providing controlled access through the property, so existing code using the class does not need to change. Dynamic read-only values. Dynamic read-only properties let a class expose something that looks like a simple attribute, but is actually computed each time it is accessed. This means client code can treat it as stable data, while behind the scenes, the class can derive the value from other fields, perform calculations, or even query external resources. It is especially useful when the value depends on changing state, such as a person's age or a bank account balance. The result is a clean, consistent interface whose internal implementation can change over time without breaking existing code that uses the property. Read-only properties let you access an attribute without changing it directly, which helps protect data integrity. If you try to modify a read-only property, the class can either ignore the change or raise an error, depending on how it is designed. This is important for keeping data consistent, such as making sure a delivery status in a shipping app matches real timestamps and events instead of arbitrary edits. By keeping the property read-only, its value only updates when the underlying data changes, giving you a stable, predictable, and easy-to-use interface. Dynamic read-only properties are useful when a class field that once stored a simple value now needs to be computed or include extra logic, such as caching. Instead of changing every place in the code that uses this value, you turn the old attribute into a property that calculates the result when accessed. The property keeps the same name, so existing client code continues to work as before. At the same time, the class gains full control over how the value is produced and can evolve its internal behavior without breaking other parts of the system. Python code. Dynamic read-only values. Use a simple person example to demonstrate a dynamic read-only property. The person has an age value that is not stored directly, but is computed from the current year and the person's birth year. When the internal current year changes, the age value updates automatically without any manual recalculation. External code is not allowed to assign a new value to age directly, ensuring that this attribute always reflects the correct computed value. The script starts by importing the date class from the datetime module so it can work with calendar dates. This allows the program to easily access the current year. Using this, the code can automatically calculate a person's age based on their birth year, rather than requiring the year to be updated manually. The person class represents an individual with two main pieces of data, a name and a birth year. In the initialization method, the name is stored in a public variable that can be accessed from outside the class. The birth year is stored in a separate variable whose name begins with an underscore to indicate it is meant to be private. This design lets the class expose basic information, like the name, while keeping more sensitive details, such as the birth year, encapsulated and protected from direct access. In this code, the person class defines an age property that behaves like a normal attribute but is calculated automatically. When age is accessed, the method gets the current year from the date system and subtracts the stored birth year, which is kept in a private attribute. This means the age value is always current and updated whenever it is read. At the same time, it prevents code outside the class from directly changing the age value. We create a new person object named Alice and set her birth year to 1990. The class constructor automatically runs when this object is created and stores her name and birth year inside the object. Because of this setup, we can later access Alice's age as a value that is calculated from her stored birth year and the current year. We first show that accessing the name attribute of the person object works in the usual way, confirming that the class behaves normally for standard attribute access. Then we display the current value of the age property, which is not stored directly but computed each time from the current year and the person's birth year. This illustrates how a property can provide a read-only, dynamically calculated attribute instead of a fixed value. When we try to set the person's age to 99, an attribute error occurs because the age property only has a getter method and is therefore read-only. This means the property is intentionally designed so it cannot be changed from outside the object. The error is caught, and a message is shown to explain that direct assignment to the age property is not allowed. The first line prints a message explaining that the birth year attribute is treated as an internal, unchanged, and protected value, accessed directly from the person object using an underscore to suggest it is private. The next line prints a message about the age property, emphasizing that the age is recalculated each time it is accessed. This works because age is defined as a computed property that uses the current year minus the stored birth year. As a result, the age value always stays up to date without needing manual changes. This example shows how to create a dynamic read-only property in a Python class using a simple person model. The class stores a birth year internally and uses the date module to get the current year. It then calculates the person's age on the fly whenever the age property is accessed, so the value always stays up to date. Because the age is defined as a read-only property, trying to assign a value to it raises an attribute error, preventing any external changes. As a result, the age is always computed dynamically, while the birth year remains unchanged and protected inside the class. Preserving existing interfaces. When you add new properties to an existing class, you need to avoid breaking code that already depends on how that class currently works. Other modules or external clients may directly access attributes, such as a customer's discount rate, and forcing them to switch to explicit getter and setter methods can cause widespread errors and expensive changes. Using properties lets you improve or change the internal logic of the class while keeping the same simple attribute-style access on the outside. This way, reading and writing values looks the same to existing code, even though the implementation behind the scenes has become more sophisticated. Properties are useful when a simple class attribute needs more complex behavior over time. For example, a bank account balance might start as a plain value, but later you may need to log changes or enforce rules like a minimum balance. By turning the attribute into a property, you keep the same way of accessing it while adding validation or logging behind the scenes. This lets existing code continue to work unchanged while giving you more control over how the attribute behaves. Using properties in a class lets you change how data is handled without breaking existing code. You might start with simple attributes for things like timeouts or file paths, then later need to compute them dynamically or enforce new rules. By turning these attributes into properties, you can add behavior such as deprecation warnings or format conversions while keeping the same way of accessing them. This preserves a stable interface, protects existing client code, and reduces the risk of bugs during refactoring. Python code, preserving existing interfaces. Use properties to keep the familiar attribute style of access while adding extra behavior behind the scenes. The goal is to let existing code continue to read and write attributes in the same way as before, so old direct attribute access still works correctly. At the same time, you can introduce validation to check values and logging to record changes, all without altering the external interface that other code depends on. We define a class called BankAccount to represent a simple bank account with basic information. Inside this class, an initialization method runs whenever a new account object is created. It takes the account owner's name and a starting balance as inputs. The method stores the owner's name in an instance variable and the starting balance in another instance variable called balance. This setup lets us easily create new bank account objects with a specific owner and initial amount of money, and then access those values through the object's attributes. We create a new bank account object for an owner named Alice and give it an initial balance of 100. This sets up the account with those starting values. We then access the balance attribute directly and print it. This shows how existing client code reads the balance value without any extra logic or validation, simply displaying the current amount stored in the account. We define a bank account class whose constructor sets up two main pieces of data: the account owner's name and the account balance. The owner's name stores who the account belongs to, and the balance is initialized from a starting value. This starting balance is converted to a floating point number, so calculations are consistent. With this basic structure in place, we can later add features like validation and logging without changing how the balance is accessed from outside the class. This part of the code creates a property for the balance attribute. When the balance is read, the property's getter runs, prints a message that the balance is being accessed through the property, and then returns the value stored in the private variable. Using a property in this way lets you add extra behavior, such as logging or validation, without changing how other parts of the program access the balance. The setter method for the balance property runs whenever the balance is updated. It first reports that an update is being attempted, then checks whether the new amount is negative. If the amount is negative, it raises a value error to prevent the balance from going below 0. If the amount is valid, it converts the value to a float and stores it in the internal balance attribute to keep the data consistent. We create a bank account for Alice with a starting balance of 100, which initializes the account with those values. Then we print the account balance. Even though the class now uses a property to manage the balance internally, the code that uses the class still accesses the balance as if it were a simple attribute. This shows that the public interface has not changed. So existing client code continues to work without any modifications despite the internal implementation changes. This script shows how to refactor a class to use properties while keeping the same public interface. At first, the bank account class exposes its balance directly, and client code reads and writes this value as a simple attribute. The class is then updated so that balance becomes a property with a getter and setter that add logging and validation, such as preventing negative balances. When the balance is accessed or changed, messages indicate that the property methods are being used. This approach lets existing code continue using attribute-style access without changes, while the class gains extra safety and behavior behind the scenes. In this lecture, you learned to explain the role of object as the ultimate base class in Python's class hierarchy, define properties using the property built-in or decorators to control attribute access and validation, and use properties to replace direct attribute access in simple classes without breaking client code. In the next lecture, Lecture B, we will go over super end methods. Thank you for your attention. See you all in the next lecture.